Okay, that's it. Okay. Hi, everybody. As Dr. Barrera said, I'm Valentina, and today I'm going to be presenting my senior seminar project on financial mathematics and its applications to strategic investing. So before I present my main project and my goals, I would like to go over some important definitions. And first of all, we have the definition of financial engineering, also called mathematical finance, financial mathematics. This is a field of study that focuses on the mathematical modeling of the financial markets. It uses stochastic processes, statistics, probability, and economic theory to do so. And it is used for structuring, creating and structuring portfolios, developing investment strategies, which is actually what I'm going to do in my project, risk management, options pricings, and many other things. This is a field of study that has been steadily growing the last couple of years, and it's actually expected to keep growing the next few years as well. Next, moving on, we have Roth IRAs. Roth IRAs are a type of retirement investment account, and you might be familiar with traditional IRAs. They are very similar, but the big difference between them is that Roth IRAs contribute after-tax dollars, while traditional IRAs contribute pre-tax dollars. Next, finally, we have mutual funds. Mutual funds are a type of investment in which you're technically investing in this basket of assets, and it usually contains stocks and bonds and other money instruments. And they are great for the average investor. Consider that usually the average investor doesn't know which stocks to buy, which bonds to buy in order to diversify their portfolio. And they are operated by professional fund managers. These are actually the people who buy those stocks and bonds for you. And on the right, we can see a graph. This is the graph of a performance of $10,000 being invested on an index mutual fund called BT Sachs. And this is actually the mutual fund that I will be working on with my project. And as you can see, it goes up to around $45,000 after 10 years without making no contributions. So now that we know a little bit about financial mathematics, I'm going to go over some of the history, some of its development. First of all, it all began with Louis Bachelier. He was a French mathematician, and he was the first person to model the stochastic process that we now know as Brownian motion. And that simply, it models the fluctuations of an asset's price. He was also the first person to publish a paper that used advanced mathematics in the study of finance. And that was actually his doctoral thesis. And for these reasons, he's now considered the father of financial mathematics. Moving on, we have Norbert Wiener. In 1923, he was the first person to prove the existence of the Brownian motion mathematically. And he also developed Wiener processes, which describe the probability distribution function of the Brownian motion. And moving on, we have Fisher-Black and Myers-Scholes. Both of them in 1973, they developed a partial differential equations formula that, they developed a formula for options pricing based on partial differential equations, which is now called the Black-Scholes model, and it's one of the most important concepts in modern financial theory. And finally, we have Michael Harrison and Stanley Pliska. They developed the fundamental theorem of asset pricing, which ensures the completeness of the market. And this is one of the main pillars of financial mathematics. And in fact, it's crucial to the Black-Scholes model. And there are also many other people who contributed to financial mathematics, but for the sake of time, I'm going to have to omit them. But now that we know about financial mathematics, I can now present my goal and my plans for my project. So the goal of my project is to use financial mathematics in order to find the best investment strategy for a single investment in the BT Sachs Index Mutual Fund with a Roth IRA, based on historical data from Yahoo Finance from the years 2001 to 2020. And to do so, I have the following plans. So first of all, I would like to develop several investment strategies develop Python programs that will simulate the investment strategies. Secondly, I would like to compare and analyze each of these strategies in order to determine which one is the best option. And finally, I would like to use the Wiener processes that I mentioned earlier in order to predict prices for BT Sachs, the index mutual fund, for the year 2021, and actually compare those results with the actual data that we have today and see how well the Wiener process is worked. So now I would like to explain some more about the investment strategies and how they work. So each investment strategy is going to invest a specific amount of money on a specific day of each month from January 2001 to December 2020. And what the Python program is going to do is going to spit a final return at the end of December 2020 with the final investment amount. So from all the contributions you made, the final investment. And in order to pick the dates for each month, they're going to follow 4 different types of distribution. And each one of them is going to represent a different investment strategy. Therefore, I'm going to have 4. So the first one is going to follow a normal distribution. So the dates in this strategy, they're all going to land around the middle of the month. They're going to be the 15, the 14, and that's because the mean that I chose was 15, and the standard deviation is going to be 5. The next program is going to follow a uniform distribution. So the dates throughout the month, they're all equally likely to be picked. So the first day can be just, it could be picked, or the 10th, it doesn't really matter. For the third strategy, it's going to follow a log normal distribution. The dates here, they're going to be around the 10th. It's most likely to get the first ones than it is to get the last ones. And finally, for the exponentially distributed program, in that one, you're most likely going to see the first days of the month. It's not very likely to get the last ones, for example. So those are my 4 strategies. And in fact, since I want to mirror reality as well as possible, I have to take into consideration several things. First of all, those are going to be fees. Second of all, expense ratios, which are different for each mutual fund, for each stock. And in this case, for BTSAC specifically, it's going to be 0.04. And what this means is that whenever at the end of the year, 0.04% of the running shares that we have are going to be deducted. And finally, we have Roth IRA. We need to take into consideration Roth IRA yearly contribution limits, which we can see in the table on the right. And those, basically, they tell you how much you can spend with how much you can invest with a Roth IRA. You cannot go over those limits according to each year. And actually, that's gonna determine my monthly investments, which you can see in the formula over here. So depending on the year, the monthly investment is gonna be that amount, that maximum amount, divided by 12, which is the number of months in the year. And I decided to do it with the maximum contributions, but you can definitely invest less than the maximum contribution. So now you may have noticed that I only coded 4 different strategies, and there are definitely many others. And in fact, there's 20 to the power of 240 possibilities. And this number comes from the fact that there are around 20 trading days per month. And there's 240 months from January 2001 to December 2020. So there are at least 20 to the power of 240 possibilities. And in fact, this number is impossible to compute. There's not enough time in this universe to compute this number. So that's why I cannot compare all the possible investment strategies. So I decided to stick with 4. And we'll see how that goes. So for my data analysis, so I ran each one of my programs 10,000 times, and I collected that data. And after doing that, I realized I need to conduct some kind of statistical analysis to compare them. And before I did that, I decided to plot the histograms for each one of them to see what kind of distributions they follow. And as you can see, none of them follow a normal distribution. Therefore, I realized that I cannot conduct certain types of statistical analysis. And in the end, I decided to stick with descriptive statistical analysis. And descriptive statistics, they consist of a bunch of different coefficients that describe given data sets. In this case, they describe 4 different data sets. And whisker plots are great ways to plot them out. So as you can see here, we have 4 boxes. Each one of them represents the different strategies. And each box individually, those are called box plots. That's the interquartile range for each one of the strategies. The crosses represent the mean. The line inside the box represents the median. The ends, those are the whiskers. The ones above there are the maximums, and the ones below there are the minimums. And as you can see in the exponential program, there are a lot of bunch of dots. Those represent outliers, and you can only see them in the exponentially distributed program. So after looking at this graph, I realized that the highest median, the highest maximum, the highest median, the highest mean, the highest third quartile, they all correspond to the uniform program. Then I noticed that the highest maximum corresponds to the log normal program. And what I definitely noticed is that for the exponential, that one has the lowest minimum, the lowest maximum, the lowest mean, the lowest everything. So I conclude that the best option is the uniformly distributed program, and that the worst option is undeniably the exponentially distributed program. So now that I have determined my strategies, I'm going to move on to the winner processes. And before I do that, I would like to introduce some important key terms to understand the next few slides. So first of all, we have a random variable that simply measures the outcomes of a random event. And they're usually denoted with capital letters. You're probably gonna see capital X, capital Y in the next slide. And there's two kinds of random variables, discrete and continuous random variables. Discrete random variables have a finite number of values, whilst continuous random variables have infinitely many values. Next, we have probability distribution. That's going to be another term, another important term. That gives us the possible values of the random variable and its corresponding probabilities. Then we have the expected value. The expected value is essentially the mean of the random variable, no more than that. And then for variance, that's the average of the square deviations of the random variable away from the mean, which is, again, the mean is the same as the expected value of the expected value. So now I'm gonna introduce the official definition for Wiener process. So Wiener process is a time continuous process that has 4 properties. First of all, its initial state is 0. Second of all, for each t, Wt is normally distributed with a mean of 0 and variance of t. Thirdly, the displacements from, for example, Wt1 to Wt2, they're independent. So wherever Wt2 goes, does not depend on Wt1. And the same thing with Wt3, 4, and 5. Wherever 5 goes, does not matter where 4 goes. And finally, Wt is a continuous function of t. So that's the definition for a Wiener process. And here specifically, I would like to prove one of the properties of the Wiener process. And the property that I would like to prove is the one of the expected value of the random variable Wt being equal to 0. And to do so, I need the following theorem and the following definition. The theorem simply lets us split the expected value for random variables in addition, so we can split it. And then the second definition is just the definition of the expected value of a continuous random variable, not discrete, a continuous random variable. It's defined by the integral from negative infinity to infinity of x times f of x dx, and f of x is simply the probability density function of the random variable x. So now I'm gonna start with the proof. So similar to what happened with Chloe, I'm gonna use proof by induction. And first of all, I need a base case. So for my base case, I'm gonna use capital X and capital Y as my independent continuous random variables. And each one of them is gonna have its corresponding probability distribution function, f of x and f of y. And then we're gonna let the joint probability distribution be capital F of x comma y. And then since x and y, they're both independent, we are allowed to split the capital F x y, so the joint probability, into just each PDF multiplied by each other. And PDF means probability distribution function. So now that we have this, we can start calculating our base case. I know this looks a little overwhelming, but bear with me. So first of all, in the first line, we're just simply applying the definition of the expected value. So here on the next, and then on the next line, we're just gonna FOIL that x plus y. On the line number 3, we're gonna split the integrals in addition. So x is gonna be on one side, y is gonna be on the other. On line number 4, we're gonna flip the order of integration of the first term. We're gonna leave the other one as it is. And then on line number 5, we're gonna split that joint PDF because we're allowed to do that because x and y, as I said, they are independent. On line number 6, since we flip the order of integration, we can now pull out this variable over here, and the same thing happens over there. And then finally, line number 7, that part, that second integral in the first term, that's simply equal to 1 by definition, and same thing happens over there. So we're just left off with that first part, and then the other part with the plus y f of y. So in that line, we can just apply the definition of expected value again, and therefore we get the expected value of x plus expected value y, and we have proven our base case. But this continues, because since we proved the base case, now we would like to do, as Chloe said, we're going to have an induction hypothesis, and we're going to have an induction step. So for the induction hypothesis, we're going to assume, so previously we proved it for n equals 2. That's why we had x and y. And we're going to prove it for all those x's, all those n's, excuse me, greater than or equal than 2. And we're going to assume that that idea is true for all up to n. And then what we need to prove in our induction step, that this is true also for xn plus 1. So we're going to let x1, xn plus 1 be, again, independent continuous random variables with its corresponding probability distribution functions. Also, we're going to have a joint probability again, and that can be split once again in multiplication because all these variables, all these random variables are independent. So this one is more overwhelming, I know. Once again, the first line, just applying the definition of expected value. On the second line, we're gonna go ahead and split that joint PDF into the multiple PDFs because that's easier. We're just gonna do that in the second step. And then on the third line, we're just gonna factor out the PDF of n+1, only that one. And then on line number 4, we're gonna split that integral in addition so that we're gonna have two terms, and in one of them it's gonna go from x1 up to xn, and the other one is just gonna be xn plus 1 alone. And that happened on line number 4. And then on line number 5, within those brackets, the first part is simply we can apply the definition of expected value, and we're gonna get this part over here, and then we're gonna leave the second part as it is. On line number 6, the expected values, they're just a constant, so we're gonna pull them out outside of the integral. We are allowed to do that. We are still leaving that second term as it is. And then on line number 7, finally, if we compute this integral here, that's just equal to 1. So we're gonna get this part times 1. That's just this part as it is. And then if we apply the definition of expected value on the second term, we also get the expected value of n plus 1. And this part, notice that they're all together. By our induction hypothesis, we can split all these n's. So we get the final step in line number 8 at the end, and we have proven our theorem by induction. So now we are not done yet. So I mentioned that I wanted to prove my property, and the property is that of the expected value of the random variable WT being equal to 0. And to do that, we're going to use the theorem. And we're going to use the fact that all those xk's, which are the random variables, they're normally distributed with a mean of 0 and variance of 1. And also we're going to use the fact that all those xk's, they're all pairwise independent. So now the expected value of the random variable that we see over here, it's defined by the stochastic process that we see here. And then we can just replace that part of the expected value with a summation with our theorem. And that we can split that by our theorem. And then if we plug in, if we know that the expected value is the mean, and over there we said that the mean is equal to 0. So those are just going to be a bunch of zeros added together. And that's just 0. And if we multiply that by 1 over square root of n, that's again going to be 0. So then we need to prove that the limit from n to infinity of EWNT is equal to 0. And EWNT is 0. So the limit is going to be simply 0. And therefore, we have proven that the expected value of WT is equal to 0. And we have proven our property. So now the fun stuff. This is very exciting. Coding the winner process on Python programming fits this graph over here. This is BT Sachs. This is a prediction for BT Sachs in the year 2021. And as you can see, these are the days. And on the y-axis, we have the stock price. The trading days go up to 252 because there are 252 trading days in 2021. And well, this is what the winner process said. And now we can compare it with our actual data from 2021 up to, I did it up to October 5th. That's why it goes up to 149. And in blue, we have the prediction, so the winner process. And in red, we have the actual data. And as you can see, the winner process does a pretty good job up to date 110, 115. And I think this is actually really good considering that we cannot predict the stock market as of today, at least. And this is just based on historical data. And I think this is a pretty good estimate. So after all my research, I came up to these conclusions. So first of all, the uniformly distributed program, that one seemed to perform best to me out of just those 4 strategies that I coded. Second of all, this is undeniable. The exponentially distributed program provided the worst result. That was the worst investment option. That provided the worst investment outcomes. Then thirdly, I know there might be a better strategy out there. It's not uniform. It's not the best strategy out there. I'm pretty sure there's another one that's better, but I cannot compute all the possibilities. So I'll never know if there's actually one that's better. There's actually probably a perfect one, but it will be hard to compute that considering that there are 220 to the power 240 possibilities. And then my 4th bullet point for future work, I would definitely like to try other investment strategies. There's so many other distributions that I can try. So that will be interesting future work and see if they outperform the uniform program. And then finally, winner processes, I conclude that they definitely provide a close estimate, considering that we cannot predict the stock market as of today. That was a pretty good estimate. And well, these are my references. Thank you so much for listening. Are there any questions or comments?
What made you interested in working in financial math?
I guess, I mean, I always liked math. And then I just needed something to combine math with because I like applied math. And then I guess I started getting interested in finance and the stock market and all that. I think that's what drew me over there. And then I found this. And I don't know, I just decided to do my research project on this because I really wanted to dig into this area. I also would like to go to graduate school on this area.
So it kind of makes sense to me that like randomly just choosing a day to invest 1/12 of your yearly maximum. It kind of seems like that would be the best way to go. But what I'm having a hard time grasping, and maybe you have a theory about this, like why does it seem like investing on the first day of the month is definitely the worst thing to do, right? That's what, because your exponential was like, mostly it was like the first possible day of the month, right?
Yeah.
So why was that? Like, do you have any sort of theories as to why that was so bad?
I'm honestly not sure, but that's definitely a trend, as you can see. I don't know. I'm thinking about all the things that happen after the first days of a month anywhere. I don't know. People get paid later on the month. They invest later. I don't know. It's a good question, but that's the only thing I can think of right now. But there are definitely other factors.
Yeah, it's something seems to be going on.
Something's going on, yeah.
Other questions for us? All right, well, let's thank Valentina again.